YouTube channel Knowledge Entertainment, and we are starting with the chapter of separation axioms in topology today. So what are separation axioms? What is their properties? What are the properties? This is the topic that we will discuss today. In the separation axioms, the first one is T naught. So a topological space, X tau. So that means X is the set and tau is the topology defined on this set X. So a topological space X tau is said to be a T naught space if for any 2 points X and Y, distinct points of X, there exists either an open set G such that X belongs to G, Y does not belong to G, or there exists an open set H such that X does not belong to H and Y belongs to H. So the space will be T naught if for every 2 points X and Y either there is an open set G which contains X and not contain Y, or there exists an open set H that contains Y but not X. So diagrammatically, what is the situation? Let us see the situation diagrammatically. What a T naught space is, we can understand it in a better way if you use diagram. So suppose here is your X tau. X is the set and tau is the topology. So what is the definition of T naught space diagrammatically? If you take any 2 points X and Y in the set X, so what you require to make this topology a T naught topology, either you should have an open set G which contains X and does not contain Y, or you have an open set H that contains Y but not X. So if even one of these two open sets you are having, your topological space will be T naught space. And a T naught space is also known as Kolmogorov space. Kolmogorov space. So T naught space and Kolmogorov space is one and the same thing. And now we will move on to some examples, some theorems related to T naught spaces. The first one is discrete space. So let us check whether discrete topological space is T naught or not. So we are talking about discrete topological space. I am talking about this space. Now look at X is a set and tau is discrete topology on X, and in discrete topology we know that every subset of X is an open set. So suppose X and Y are two distinct elements of X. To make this topology T naught, what we need? We need either an open set containing X and not containing Y, or we need an open set containing Y and not containing X. And that is very easy to trace in this case, because every subset of X is now an open set. So let us talk about this set, the singleton set X. It is, since X is an element of X, this singleton set X is a subset of X, and since every subset of X is an open set, this is also an open set. So this is our required open set, you can say G, such that X belongs to it and Y does not belong to it. So here you are having an open set containing X and not containing Y. In fact, we are also having an open set Y, singleton set Y, that contains Y but not X. But we need only one of these two. In fact, both are existing here, but one of them will work. So if I consider any one of these two, I can take this one, G, singleton set X, I can take H, singleton set Y, and that will be more than enough to prove that the discrete topological space is T0 space. So this is the first example. So after discrete topology, it straightforward comes to our mind, what about indiscrete topology? Is it T0 or not? So let us check whether indiscrete topology is T0 or not. In discrete topology, we are having in topology only two members, that is phi and the set X itself. So there are only two open sets. One open set is phi and another open set is X. There is no third open set. Every other open set, if you will take, it will not be an open set. And now, if you take two elements X not equal to Y in the set X, since we are having only two open sets, the first one phi, it does not contain either of these two, and the second one contains both of these. So that means it is not possible now to find an open set which contains X and not contain Y, or an open set which contains Y and not contain X. So that means in this case, in discrete topology case, we are not having an open set containing one of these two elements and not containing the other element. That means this topology is not makes the space a T0 space. So that means X with I am denoting IY for indiscrete space. So X with indiscrete topology is not a T0 space. So this topology is not a T0 topology. So let us move on to another example. There is a famous topology, you can say topological space, known as Sierpinski space. So let us see about Sierpinski space, if it is T0 or not. So you know what is Sierpinski space. Your set X contains two elements, A and B, and your topology in case of Sierpinski space contains three sets. One is empty set, other one is the whole set X, and the third one may be either the singleton set A or the singleton set B. So let us take the singleton set A. So this is now Sierpinski space, and let us check whether it is T0 or not. Now we need two distinct elements from X, and X is having only two elements, so we will have to work with these two elements only. So take A not equal to B belonging to X. We in fact wanted two distinct elements, and there are only two elements distinct. So we have taken these two. Now what we need to make this topological space a T0 space, either there should be an open set containing A and not containing B, or there should be an open set containing B and not containing A. And we are having only three open sets. The first one contains none of these. The third one contains both of these, but the required set is the second one. This set A, since it is a member of Tau, so it is an open set. So this is the required open set G, which contains A, but it does not contain B. So that set will work and the topology will become T0 space, or you can say T0 topology. So this is third example, and now we will move on to another important topological space, that is a set X with cofinite topology defined on it. So let X be a set and tau be cofinite topology defined on the set X. So let us see if X tau is now T0 or not. That means this topology is T0 topology or not. That means the space is T0 space or not. So once again we take two distinct elements. So let X and Y be two distinct elements of X. Look at this singleton set X and take its complement now. A set in cofinite topology is open if and only if its complement is a finite set. This set, I am naming this set as G. Now look at the complement of G. G complement means X complement and once again complement. And we know that complement of a set is the same set, so it is the singleton set X. That means G complement contains only one element. That means G complement is finite. So this means G complement is finite. Since G complement is finite, so G must be an open set because it is cofinite topology. So this means your G must belong to the topology Tau. That means it must be an open set. Now what is G? G is your set complement of the singleton set X. That means G contains everything from the set X other than small x. So this X does not belong to G. And since it contains every element other than X from the set X, that means Y must be in this set. So Y belongs to G. Once again look at it, what you have obtained. You have an open set G. You have taken two distinct elements X and Y. You have an open set G such that G contains one of them and G does not contain the other of them. That means for two distinct elements X and Y, you are having an open set G containing Y but not containing X, and that is more than enough to show that the topological space X tau with tau as a cofinite topology on X is a T0 space. So this was another example, and now we will move on to the next property of T0 spaces, Kolmogorov spaces. The property is let X tau be a T0 space and tau is a subset of tau dash. That means tau dash is a finer topology than tau, or you can say tau is coarser than tau dash. Then X tau dash is also T naught space. So that means if a topology is T naught, then any topology finer than that is also a T naught topology. This is a property that we are going to prove now. So what we are to do, we will take two distinct elements from the set X, and we will try to find an open set in tau dash which contains one of them and does not contain the other of them. If we are able to find such an open set, that means we will be able to prove that the topological space X tau dash is a T naught space. So first of all, we start with taking two distinct elements of X. So let X and Y be two distinct elements of the set X. Now, forget about this topological space. We will talk about this topological space X tau. It is given to be T naught space. X and Y are two distinct elements of X, and X tau is a T naught space. That means by definition of T naught space, there must be a tau open set G containing one of them and not containing the other of them. So without loss of generality, we suppose that there exists an open set, tau open set G, which contains X and not containing Y. So therefore, there exists a tau open set G such that X belongs to G and Y does not belong to G. Now, tau dash is finer than tau. That means every tau open set is also a tau dash open set. G is tau open set. G is tau open set. I have written it repeatedly. G is tau open set, and every tau open set is tau dash open set. Therefore, G is also tau dash open set. So I am rewriting this sentence, the last one, using tau dash here. Why? Because every tau open set is tau dash open. So tau open set G is also tau dash open set G. So what you are going to get, there exists a tau dash open set G such that the set G is same. This is the set G which was tau open, and now it is tau dash open, but the set G is same. That means G still contains X and G still does not contain Y. So such that X is in G but Y is not in G. So now look at what we have done. We have taken two distinct elements X and Y from the set X, and we have obtained a tau dash open set G containing one of them and not containing the other of them, which makes the topological space X tau dash as a T naught space. So that means if a topological space with topology tau is T naught, then the topological space X tau dash, where tau dash is finer than tau, is also a T naught space. Now we will move on to the next property, or you can say next example. We have seen discrete topology, we have seen indiscrete topology, we have seen Sierpinski space, we have seen cofinite topology. The case of co-countable topology is very much similar to that particular case of cofinite topology. And there is another question now in our mind: what about usual topological space? So let us see usual topological space, if it is T naught or not. So we are having R, the set of real numbers, and usual topology on the set R. Usual topology, you understand what usual topology is? Usual topology means the members of U are either open intervals in R or unions of open intervals in R. So, first of all, let me write what U is. U is the collection of open intervals in R and their possible unions. So this is your usual topology. And now we have to check whether it is T naught or not. So where we are to start with? Once again, let X and Y be two distinct elements of R. That means X and Y are two real numbers. So we can be clear to understand it through diagrammatically. Now, diagrammatically, X and Y, this is your real line. And since X and Y are real numbers, so we can represent X and Y on the real line. Now, take the distance X minus Y, this distance. Take this distance mod of X minus Y and half of that. Let it be delta. So, this is your delta, or you can say this is your delta. Now, consider the open interval X minus delta, X plus delta. You can also take Y minus delta, Y plus delta. That will also work. So I am taking X minus delta, X plus delta open interval, and I am naming it as G. Since every open interval is an open set for usual topology on the set of real numbers, so this G is also an open set. So diagrammatically you can see your open interval is like this, and it is very much clear now that your X belongs to this open interval and Y does not belong to this open interval. So this G is an open set. So therefore G is an open set because it is an open interval. So it is an open set such that this open set G, or you can say open interval G, it contains X and it does not contain Y. So for any two distinct elements X and Y, for any two real numbers you can say X and Y, you are having an open interval, that means an open set G, which contains one of them and not the other. If you have taken Y minus delta and Y plus delta, then your interval will have contained Y but not X. Whatever the case, we are having an open set containing one of the elements and not containing the other element, which will make this topological space a T-naught space. So that means the usual topological space is also a T-naught space. There are other examples. I can take the topology induced by a metric space. So let X top be topology induced by metric D on X. Metric D on X. So let us see if it is T-naught space or not. So what we have to do? Once again, we will take two distinct elements X and Y from X. The proof is almost similar to the previous one. the only difference is earlier we have taken the distance between x and y, and now we are taking d of xy. D of xy, d is the metric. D is the metric on the set x, and instead of taking the distance mod x minus y, we are taking dxy, and once again half it and take it as delta. Now consider the open ball B centered at x and radius delta. Diagrammatically, you can see what we are going to do. There is x, there is y, and dxy is nothing but the distance between x and y, if honestly speaking. So this is your dxy, and we have taken half, and now we have taken this delta, and now we are considering this ball. You can take by delta, that will also work. So I am taking bx delta. So bx delta is this open ball, and we know that every open ball is an open set. So this open ball, if I name it as G, then G is an open set. And from the diagram it is very much clear that your x belongs to G and y does not belong to G. So G is an open set such that G contains x and G does not contain y. So that means we have obtained an open set G containing one of the elements and not containing the other, which is sufficient to show that the space is T0 space. We'll move on to another example. So I'm taking another example. You must have seen this example when you have started the course of topology. So n, we know that n is the set of natural numbers, and I'm taking the topology. This is our set x now, is the set of natural numbers, and topology is phi n, and all subsets of the type 1, 2, 3, 4 and so on up to n, where n is any natural number. That means, to be more clear, this tau is containing the set phi, the set n, the set of all natural numbers, then singleton set 1, then 1, 2, then 1, 2, 3, then 1, 2, 3, 4, and so on. All the sets of this type are the members of tau. Now we are once again to check whether this is a T0 space or not. So let there be two members. Since x is the set of natural numbers, so your x and y are now natural numbers. So let us denote them by m and n. Let m, n be two natural numbers, or you can say the members of x. Since the set of natural numbers n follows the trichotomy law, so either m is less than n, or m is equal to n, or m is greater than n, but we have taken m and n as two distinct elements. That means the second possibility has gone. So what you are left with, either m is less than n or m is greater than n. Without loss of generality, we suppose that m is less than n. Now consider this set 1, 2, 3, 4 and so on up to m. This is a set of this kind. So that means this set is a member of tau. So this is a set, suppose let it be G. It is a member of tau, and since it is a member of tau, it is an open set. So G is an open set such that your m belongs to G and n is greater than m, and no natural number greater than m is a member of G, so N is also not a member of G. So you are able to find an open set G which contains one of the two elements M and N and not containing the other, and this makes that the space X top is a T naught space. So I'd like to stop this video here. In the next video we will learn something more about T naught spaces, and then we will start with T1 spaces known as Pratchett spaces, and then T2 spaces known as Hausdorff space, and so on, T3, T3 and a half, T4, T4 and a half, T5 spaces. So till then, revise this lecture once again, make your notes and wait for the next video. Thank you once again.